Have you ever just stopped and wondered how thousands of, mindless ants can team up to build an incredibly complex nest? Or maybe even weirder, how a bunch of simple computer circuits can suddenly learn to write poetry? Well, this is the great puzzle of emergence. This idea that simple parts, following simple rules, can create something completely new and unexpectedly complex. So let's dive in and try to unravel this fascinating mystery.
And this isn't just a question from one little corner of science. It's a fundamental pattern we see absolutely everywhere. It's the core idea behind that famous scientific paper, More is Different. This concept that you just can't understand the whole system by looking at its individual parts alone. Something else is going on.
I mean, just think about an ant colony. There's no CEO ant. There's no master architect handing out blueprints. Nope. Each ant is just following a few super local rules, like follow this scent trail or carry that little piece of dirt. And yet, somehow, together, they create these amazing structures and show this incredible collective intelligence.
Or here's one we've all felt, a traffic jam, right? Every single driver is just trying to get home. They're making their own little decisions. Speed up, slow down, keep your distance. But then all of a sudden, these local actions combine to create this massive, slow-moving wave. A wave that nobody wanted and that no single person is in control of.
And that brings us right up to the cutting edge. Think about large language models, LLMs. At their core, they're made of pretty simple digital neurons. But when you scale them up, when you get billions of them working together, they suddenly develop these surprising new abilities. They can get jokes, they can write code, things they were never explicitly programmed to do.
So the thing is, while we can see all these examples plain as day, science has been scratching its head for decades. We haven't had a single, unified theory to explain how, and crucially, when this leap from simple to complex actually kicks in. Well, until maybe now.
And this brings us to a really exciting new idea. It's a framework called Constraint-Resonance Emergence Theory, or CREAT for short. The whole point of CREAT is to finally provide that missing unified explanation, one that's designed to work for everything, from physics and biology all the way to AI.
So what makes this theory so different? Well, previous ideas were great, but they often just explained one little piece of the puzzle. They were often specific to one domain, or maybe a bit more philosophical. CREAT's goal is way more ambitious. It wants to be a single, testable story that works across all domains. And here's the kicker. It aims to predict the exact moment when emergence is going to switch on. So how in the world does it claim to do all that? Well, the answer is all about a powerful feedback loop. This is the engine at the heart of the entire theory.
Okay, let's break this loop down. It all starts at the bottom, at the micro level. You've got fast, local interactions. Think of our individual cars on the highway. Now, these little interactions start to amplify upwards, creating medium-scale patterns, like small clusters of cars slowing down. If the conditions are just right, this creates a stable, large-scale pattern, the traffic jam itself. This big pattern is what the theory calls a constraint. And here is the absolute key. That macro-level jam then feeds back downwards, and it starts constraining the behavior of the individual cars, reinforcing the very rules that created it in the first place. It becomes a totally self-sustaining cycle.
CREAT has a special name for this tipping point. It calls it resonance. This is that magic moment when the feedback loop just locks in. The upward flow of influence from the parts and the downward flow of influence from the whole, they snap together into this powerful, stable cycle. And at that point, the system is no longer just a simple sum of its parts. It's something more.
And get this isn't just a fuzzy idea. It's a measurable condition. You can think of gain as the strength of that feedback loop. If the gain is less than 1, any little pattern that forms just fizzles out. But the second that gain hits 1, it means for every bit of influence going up, an equal amount is coming back down. The loop becomes perfectly self-sustaining. The system literally tips over into a new emergent state.
Okay, so that's the theory. But does this abstract idea actually work for the real-world examples we started with? Well, the theory's authors say yes, and they've got specific, testable ways to prove it.
You can really see how this applies across the board.
For flocking birds, the theory says the global direction of the flock, the heading, resonates with the local rules for alignment. And you can test it. You'd see a sudden drop in directional noise once the flock hits a certain density. For traffic jams, the big wave resonates with all the local braking events. You can test this by looking for something called hysteresis. That's when the jam sticks around long after the car that started it is gone. And for LLMs, a high-level, hidden program resonates with its internal connections, which explains that sharp, sudden drop in air when a model gets big enough. It's like a new ability just clicks on.
And this, right here, is what makes Crete a potential game changer. It's not just a nice story. It's a set of claims you can actually test in a lab or in a computer simulation. It's trying to turn emergence from a cool philosophy into a real predictive science. So this leads to some really specific, bold predictions. It says there are measurable tipping points, these critical numbers. It predicts that right at that tipping point, the information flowing up from the parts and down from the whole becomes equal, perfectly symmetrical. It predicts that sticky hysteresis effect we see in traffic jams. And, this is fascinating, it predicts that the easiest way to break an emergent pattern isn't to mess with the little parts, but to disrupt the big, high-level pattern itself. So what does all this really mean? Well, if this theory holds up, it gives us a fundamentally new lens for looking at, well, almost everything, from atoms to economies to consciousness. This quote from the original paper just nails it. It says that the big pattern, the flock, the jam, the idea, it starts out as just a side effect, an epiphenomenon. But once that resonance is achieved, it becomes a real powerful force. It becomes a cause in its own right. The traffic jam is no longer just the result of slow cars. It becomes the reason the cars are slowing down. The pattern becomes the cause. So to wrap this all up, CRET offers us this powerful toolkit. It gives us a single, repeatable flow diagram, that up-down feedback loop. It gives us a measurable threshold, that gain of 1, and it gives us clear experimental signatures to go out and look for in the wild. It basically takes the slogan "more is different" and turns it into a real scientific program.
And that leaves us with one final, pretty mind-bending question. For decades, emergence has been this thing we just observe and marvel at. But if we have a theory that can actually predict it, could we start to engineer it? Could we design new materials, new organizations, or even new kinds of AI with specific, desirable, emergent abilities, all by understanding and tuning this fundamental feedback loop? That's the incredible promise that a theory like this holds out.